Okay, thank you very much for the introduction, Georg. As you already mentioned, this talk will be about ALTO, a storage format for sparse tensors. Just a quick slide about Intel PCL, Parallel Computing Labs, where I'm currently at. It's mainly about the hardware and software co-design, especially application-driven. So what do the customers need? Also in collaboration with them, and how to improve and optimize the performance of those applications for them. And target domains are, of course, like basically everywhere nowadays: machine learning, HPC in general, and data analytics. So about this talk, I will start with a background and motivation, of course. Also going into detail a little bit about the state-of-the-art tensor formats we have right now. Then I'm going to introduce the ALTO storage format and show you some results and performance evaluation on it. Also, if you have any questions, feel free to interrupt me at any time. I'm happy to make this as interactive as you wish. So as you might know, for many application domains nowadays, we have a lot of data, massive amount of also high dimensional and sparse data. Is it in healthcare or finance or data analytics or just simple mathematics? Or for example, in AI, like recommendation systems, you could have like multidimensional matrices representing user databases or demographic informations or just consumer preferences or ratings for products like for Netflix and Amazon. So those high dimensional data sets, of course, have diverse shapes and data distributions, as well as the sparsity pattern can be totally different. Here you see a few of the sets we did our experiments on, and we have a huge variety in density here from 10 to the -2 to 10 to the -15. So it's really challenging to, in some way, efficiently encode all of them and represent them, and not just for one specific type of tensors. So the fundamental problem in sparse tensor computation is how to store, how to group, and how to organize all of the non-zeros. And here we're facing different goals. First of all, of course, we want to reduce our tensor storage. We want to improve our data locality. On the same hand, we want to increase the parallelism, and in the best case, of course, decrease workload imbalance and have a almost non-synchronization overhead when doing parallelization. The problem here is that those 1, 2, 3, 4 goals are often conflicting to each other. So for example, we can reduce the synchronization overhead, but this may increase our memory usage, or we can improve the parallelism, but this may decrease data locality, for example. Now going to the more mathematical side here. So for this work, we mainly looked at the MTT-KRP algorithm, which is a common kernel in many tensor applications, and also the most expensive part for tensor decomposition with ALS, alternating least squares. So we also did or used ALTO for the full tensor decomposition algorithms, but all the results you see in this set of slides is all based on the MTT-KRP kernel, which consists basically of 2 different steps. We have our tensor matricization or reshaping to get a 2D matrix out of our multidimensional tensor, and a Khadri-Rao product, which is a column-wise Kronecker product. And the challenge here is that it's really hard to efficiently compute all of this for all dimensions and not just for one. So because you have different locality patterns for each mode, normally you can have update conflicts in one row for or for the factor matrices. And of course, you can always have load imbalance across the different workloads for the different threads. Now, looking at a super simple example to explain the different approaches. Here you can see a 4x8x2 tensor. So we have 3 dimensions, the I dimension, the j, and the k dimension. And you can slice each tensor dimension in so-called fibers. So in our I mode, we have 4 fibers. That's our 4 here. In the j direction, we have 8 fibers. And in the end, our k mode has 2 fibers here and a dimension of 2. So this would be our 4x8x2 tensor. Now I put all my drawing skills together and added some non-zeros in here to show you like a 3-dimensional representation of this. And to make it a little bit easier, we have this also like flattened out tensor here with the 2 k fibers in the front and in the back, showing 3 non-zeros here and 3 non-zeros at k equals 1. And this tensor, like any other tensor, now has to be stored in some format, right? And we basically can classify 3 different classes of those formats. One is a list-based, the other one is tree-based, and block-based formats. So the first one is mode-agnostic, so it doesn't matter in which way it's ordered. The tree-based is mode-specific, and block-based again is mode-agnostic. The most commonly known probably is the coordinate format, is list-based format. So we just have for each dimension 1 index to uniquely identify where our non-zero is in the tensor, which is the de facto standard for many libraries, right? The CSF format, which stands for compressed sparse fiber, is a tree-based format. And you can think of it as a multidimensional CSR or CSR format, basically. And here, as I already said, it depends on the mode. So we can start creating our tree in this example with the K mode, but we can also start, like in this example, with the I mode, and based on this, we get different representations of our tensor and also different characteristics like locality. So doing the math, just by the statistics, we could get 6 possible representation, right? Because we're 3 different nodes, 3 times 2 times 1. But in practice here, we would only need 3 different representations because for the MTT-KRP, we would store just 1 mode or 1 representation per mode. So 1 for I root mode, 1 for K as a root mode, and 1 for J as a root mode here. So this definitely will or can increase the storage on the one hand, but may give us better performance on the other hand. And last but not least, we have the block-based format. Excuse me, which can be HiQ in this example, which stands for hierarchical coordinate format. And here we put our non-zeros, or we segment them into blocks and have two different kind of indexes, a block index and an element index. The block index identifies each block in our tensor, and the element index, the element, the non-zero itself within one block. The benefit from this is that our subspace in one block is much smaller than the whole tensor, right? So the index for our element can be much smaller than the index for our blocks. So this is an example for a 2x2x2 block, block-based format. So one block can have at top 8 different elements. So here we would be fine with using, for example, a 3-bit for identifying one element inside one block. So even though here in this example, it looks like we need much more storage, normally a block-based format gives us a much more compressed representation of our tensor, since we only need the size of our element per index and don't have the large data for our block indexes. But, and here we already have a good example for this, the characteristic of our tensor is really like the efficiency of our storage is really dependent of the density and shape of our tensor. And for this, I brought you another graph here. So you can see different tensors across our x-axis. And I put the density of those tensors also here above. So we can see, even though, of course, all of them are sparse, I color-coded them a little bit, and the orange ones are hypersparse, or definitely more sparse than the one in green. And the box plot shows the distribution of our non-zeros per block when using a block-based format. And here we have a block size of 128 times the dimension. So for a 3-dimensional or 3-mode tensor, it would be a block of 128 times 128 times 128. And also know that this is a log-based scale. So we can see that with increasing sparsity, which would be here on the right, Amazon, Reddit, NEL1, the number of non-zeros per block basically go down to 1. Here we have something like 2 or 3 maybe in one block, but for high sparsity tensors, it's not really efficient to use something like this representation because we only have one non-zero in a block and therefore need more data and don't have any locality we can use here. So block-based formats might not always be the best choice here. Summing this all up, of the state-of-the-art approaches, there's no holy grail so far. We have like the list-based COO format, which might give us a better finer granularity and therefore a better load balance. But on the other hand, suffers from conflicts, while the mode-specific CSF format needs to store multiple copies of our tensor to work efficiently. And the haiku format, on the other hand, introduces work imbalance because we cannot really balance the number of elements per block, or we have to do like multiple runs to see what's the best combination for our parameters. And so this is all semi-optimal, let's put it this way. And also, since CSF and haiku always introduce other disadvantages, the COO format remains basically the de facto standard, right? So that's why we then came up with ALTO, which stands for Adaptive Linearized Tensor Order. And ALTO maps the multidimensional space into a linear space and vice versa using a data-aware encoding scheme. What does this mean? So first of all, we're mode agnostic due to this linearized index for each non-zero. Also have a fine granularity. We can have a compact representation using only the amount of bits we actually need per mode. So this not only reduces the overall memory traffic, but also decreases the number of transactions, of memory transactions we need. We have improved data locality, not only across one mode, but across all modes, because the neighboring points in our multidimensional space are also neighboring in our resulting linear space. And due to the fine granularity of having each non-zero mode agnostic, we can have a perfect work balance and partition our workloads, and therefore have an effective scaling and low overhead for conflict resolutions. Yeah, and due to the data awareness, so by finding out or knowing the reuse factor for each partition, we adaptively choose the conflict resolving by either doing this atomically or with local memory, which gives us a data-aware synchronization to put then ALTO together with the other ones in this table. We can see it actually satisfies all our requirements we had before, we've seen before. So we have a maximized load balance, improved locality, are scalable, and have a mode agnostic representation of our tensor. This, as a little sneak peek, shows the ALTO performance compared to not only one different approach, but actually the best mode agnostic and best mode specific approaches. So imagine this as an oracle, always choosing the best for each tensor we had in our experiments. So orange is mode agnostic as a baseline, and ALTO is our blue line here. And you can see as geometric mean, we actually obtain a 8x speedup on our cascade-like system here with 2 sockets against the best mode agnostic one, and 1.7x of performance speedup compared to the best mode specific tensor format. But not only the performance is better, also when looking at the compression ratio on the right, here compared to the mode specific and a lot of storage needing best mode specific mode, we have a compression ratio of only 25% of data needed, of storage needed, and still like only 2/3 of the normal best of the best normal mode agnostic tensor format. So we get better performance with less storage, win-win situation in that case. So as an example, how ALTO works, how the encoding and decoding works, we go back to the example before, look at the same tensor with our 4x8x2 dimensions. And 4x8x2 is 64 elements can be in here theoretically. So we somehow need to encode a 64 element linearized space, 2 to the power of 6. So we need 6 bits for encoding this. And now the trick about this is that we shuffle those bits or arrange those bits in a way that we can keep the locality by always dividing or like encoding space of the longest mode in here. So that's why we start with our J mode. In the next bit, we would still encode our J mode since it's the longest mode. Then it would be only 2 more rows. So now we would encode our I mode with 4 dimensions, or a dimension of 4, and so on, until we have our full ALTO bit masks of the 6 bits I mentioned to encode the whole space. And then we would just linearize it. Super simple, and would get a representation like this. For each value, a 6-bit index value. So as storage, we actually would only need number of non-zeros times 6 bits in that case. So having this mode mask we just calculated before, we would use it with simple bit manipulation instructions to compress those 3 indexes of our dimensions into one ALTO index, and can actually use exactly the same mode mask for just decoding it again and getting a representation of all our indexes as integers, for example, or whatever we need. So having our ALTO representation. And now we want to do this, of course, not only for one core, but we need multiple partitions. Now we can simply divide our list, our ordered list of non-zeros into the number of cores we need and into the number of partitions. And therefore, we don't have any of our non-zeros duplicated. And we create 2 subspaces out of those 2 partitions here. One forming a subspace for those 3 elements, and the other one forming a subspace for those elements. So even though we don't have any duplicate non-zeros, of course, there's a overlapping space in our 2 subspaces, which is actually the contrasting thing to the prior work we saw with CSF and Haiku. They don't have any overlapping subspaces, but are therefore imbalanced. We have this balanced partitioning, but get this overlapping subspace, which means there has to be a conflict resolution. And the special thing about ALTO is that it's actually choosing the synchronization or the conflict resolution dynamically based on the data reuse of the target tensor. So if we have limited or no data reuse, we directly do atomic updates as conflict resolution. And otherwise, and this is actually the case where we most benefit from this ALTO format, we simply keep local copies for each thread, for each partition, and afterwards do a parallel pool-based reduction. So how does it look all together for the MTT-KRP? This is an excerpt of the paper. We go through all lines of our matrix, or for all our non-zeros in that case. We do a delinearization with a mask. So we get our 3 indexes with only 1 memory access. And then for each element per rank, for each rank element, we either do our work with an atomic update, or as we've seen with this temporal storage based on the reuse. So if we have this first case here with the temporal storage, we would need another reduction in the end. And here we just go through all of our intervals check if there is a conflict, and in that case, we accumulate everything on a global base. Here we don't need any atomic instructions since we're doing this parallelization on the on our intervals and not the modes. So this actually gives us quite a decent performance this way if we have a high reuse. Otherwise, it makes sense to directly have this atomic updates. So now looking at the numbers in a more detailed way, we did the experiments all on this Cascade Lake 8280 with 2 sockets, fixed frequency, no special optimizations besides telling the compiler to use AVX512. And we used all threads, so 2 threads per core, hyper-threading on, and pinned those threads with liquid. As configuration, we used double precision values for 64-bit for all our data values, and took the average of 100 iterations for 15 different tensors, which most of them you've seen before, ranging from very small, like only 3 million non-zeros and the size of 52 megabytes, up to multiple billion, and our largest tensor was more than 100 gigabytes. And then we compared ALTO to the previously seen formats, coordinate and hierarchical coordinate format, both part of the party library and the splat library, which uses the CSF and the special tiled CSF format, which were up to now the fastest versions, at least we've known about. Okay, so here you can see all the tensors, the 15 tensors, ordered by both number of non-zeros and the reuse. So on the left side, we have tensors with a high data reuse during the NTT-KRP, and on the right side, a limited or medium reuse. And color code for COO, haiku with different super block sizes, so 2 to the power of 10 and 2 to the power of 14, tree-based versions, and blue is ALTO. And this is all the speed up compared to the sequential ALTO version. So higher is always better. And we can see not only that we can actually reach a 47x geometric mean speed up for ALTO in all the cases here on the right, which is 84% of the theoretical speed up. And still not too bad, 22x speed up for the cases where we don't have that much reuse. But more importantly, we can see that in almost all the cases, ALTO outperforms all the other formats by far. There are 2 cases where ALTO is actually not the fastest due to the characteristics of those tensors. But looking at the variation of the CSF format, for example, you can see you don't have a general rule of thumb that it's medium or good or bad. It really depends highly on the sparsity of the shape, while ALTO is throughout all tensors close to the best or the best. Yeah. Also, if you see something like not supported, this is due to 5D. Those are 5D tensors, so haiku is just not capable of processing tensors with 5D. And if there are no numbers, we were not able to run the run the computations due to a lack of memory, which was mostly the case for CSF, since it needs more memory than the other cases. Looking at the tensor storage, on the other hand, after performance, we now see the storage here compared to COO as baseline. So the red line here is always the storage requirements for COO. There are multiple things you can see here. So this means also lower is better. We can see that ALTO always needs less format storage than simple COO. We can also see that the mode-specific formats, CSF, CSF tile, always need significantly more storage than COO. That's just since we need multiple copies, as we've seen before, for each mode. So not a big surprise. And also tiling itself needs a little bit more. And finally, the haiku memory conception is really depending, as we saw before, on the distribution of our non-zero elements, mostly also on the block size, but mostly it's about the distribution. So if you remember the tensors we saw before, which are highly sparse, like Reddit and Amazon, you can see the storage requirements for haiku, the orange and the gray, are actually higher than COO, while for more nicely shaped tensors, NIPS, Uber, Chicago, they're much lower, sometimes even lower than ALTO. But again, here you can see for the general case, ALTO gives you as geometric mean the best for all cases. Yeah, that's the high sparsity cases I talked about, Reddit, Amazon, LD, Delicious. Here you can see the haiku format is not beneficial at all. Okay, but you might wonder about the generation cost as well, because maybe it needs a lot of time to just get from a COO format to ALTO. But also this is not the case. In most of the cases, ALTO is more than an order of magnitude faster than the block-based format. It actually decreases the costs of sorting, since it's only sorting in a linearized space, while the CSF or block-based formats have expensive clustering and scheduling of the non-zeros. That's all things we don't have to care about. So for all those tensors, the creation of the special format is faster than the ones we compared it to. And in absolute numbers, we're talking about only not even 1% of the overall runtime for format creation. Another thing, okay, yeah. So the CSF format actually already is generated from pre-sorted tensors, but it's still slower. So nothing we really have to cover. So as a conclusion, ALTO as a new format can efficiently encode sparse tensors, no matter what dimension they have, in a mode-agnostic way, giving you a single representation of a sparse tensor. And by doing this, it even outperforms an oracle of choosing the best currently state-of-the-art formats, no matter if it's block-based, tree-based, or coordinate-based. Why? Because we have a really good workload balance by this fine granularity. It has adaptive synchronization, and while using bit manipulation instructions, compact encoding. This approach is really scalable up to 84% for the high reuse cases. When looking at all of them together, we get to 63% of parallel efficiency, while being almost 8 times faster than the best general formats. and keeping the storage requirements by less than 25% of the best mode specific formats and 63% of the general best formats. For future work, and this is actually already work in progress, we're working on a distributed memory version of ALTO, so using MPI on multiple nodes. Also, a version for porting it to GPUs. This is mostly done by the colleagues from University of Oregon. And after going through some inspections from the legal department, we're hopefully able to also open source the code within the next weeks, and then provide everything as a library, as Splat or like Splat and like Party, so user can simply include the library and use their functions to provide a general set of algorithms and kernels for tensor decomposition. And with this, I want to thank you for your attendance. If you have any questions, now is the time, and the preprint is available at Archive. Yeah, have a look at it if you're interested. Thank you.
Thank you, Jan, for this interesting talk. Are there any questions? You can use the raise hand feature of Zoom if you like, and then unmute yourself and speak up. So I have a small question. So maybe just to get this right, if you compare the COO format, that's like the baseline format for everything, where I would need using integer, 4-byte integers as indices, I would use 16 bytes per entry for the sparse representation. And with ALTO, let's assume the 6-bit representation that you've been presenting on slide 28, I would need 8.75 bytes per entry. That would be the savings in memory if I can use a 6-bit mask, right?
In theory, yes. In practice, we normally, since even though we have all those bfloat and int8 or whatever data types nowadays, all the memory accesses we know are working best with something like 32 or even 64-bit elements. So what we are doing is we always using a 64-bit ALTO mask if that's enough. And if not, we're directly going to 128 bits. So we actually only differentiating between 64-bit or 128-bit, since in theory you could less bits for most of the cases, but just using simple 64-bit is giving you the best performance.
Okay. Christy.
Yes, so I have a, yeah, it's along the same line actually. So for COO format, you basically also use 64 bits, right?
Yes, yeah.
And also, like, if you look into the code, for example, if you see, so I think it was in slide 30 or something.
Yeah, sorry. Here we are.
So basically, even if you save, for example, the data traffic, like by doing this compression, basically what you would save is in this I, J, and K, right?
Exactly.
But this would mean like if you are using a COO format, right? So so COO format, I would need 3 times 64-bit, but in your case, maybe only 1 64-bit, right?
Yeah, that's completely right. And in most of the cases, oh, sorry, I didn't want to interrupt you. Go ahead.
So what is the value of R you always use?
We normally work with 16, with a rank of 16, just because you can do easy SIMD vectorization. And I'm not like a field expert in MTT KRP or tensor decomposition, but as far as what we've heard, is that the rank you normally use in practice is highly dependent on your application, and normally ranges between 1 and 100.
But in the worst case, like the maximum speed up, if you look into the roofline model, it should be something around 2x, right? Because you say, for example, this 3 indices, right? Instead of 1, in ALTO you have 1. So basically, I would expect if there is no reuse, for example, in A, B, and C, which is the case, for example, if you have high sparsity pattern, you would expect only, for example, 2 times speed up, right? At most, COO format. Or I am totally wrong, maybe.
So the one case is with high reuse or with a lot of reuse. We know that our partitions with 112 partitions are actually mostly small enough to fit in L2 cache. So we're working mostly from there. With the cases where there's no reuse,
you would need to load A, B, and C anyway, right? Load and store, for example, A, if there is no reuse, because reuse is happening in B, C, and A matrices, to say, right?
Yes.
So you would anyway need 8 bytes for B, 8 bytes for C, and 16 bytes for A, which means 24 bytes. This would be required even whether it's ALTO or COO, so if there is no reuse. And 8 bytes for val would also be needed because there is no reuse. So yeah, then this is there for 16 times because your value of capital R is 16, but then you save 16 times like some 40 bytes, and the saving is maybe less than 1.5x or something, or even less than, right? In data traffic, at least.
And data traffic, yeah, you're leaving out the conflict resolution in that case, right? Because if also with COO format, you tend to have a lot of conflicts, which gives you additional overhead.
Okay, that could be okay.
So this is why in those cases, you see even for those for the limited cases, and in most of the cases, you don't even get a speed up of 5x or something, even though you're running on 56 cores, because the highly irregular tensors here like make it really hard for you.
Okay. Yeah, thanks.
But there is something like an optimistic best case roofline limit, right? So if you assume that the tensors are large enough, so there's no pure in-cache computation, and you assume that every matrix only has to be read once or read and written once, then you can give an optimistic roofline limit for this computation, right?
I mean, I don't have one, but I agree. Yeah, you should be able to give one. Yeah.
All right. Any more questions? All right, then. Thanks again, Jan, for this talk, and see you next time for the next seminar. Bye-bye.
Thank you very much. Bye.